Okay, now we'll start the product of subgroup and Lagrange's theorem. And these are two important concepts. So then how to define the product of subgroup? So in that case, what we know, the union of two subgroup may not be subgroup, whereas the intersection of any two subgroup is a subgroup. So first we'll recall some facts. Let H and K be two subgroup of a group G, be two subgroup of a group G. Then we define the product HK. This is equals to HK such that H belongs to capital H and K belongs to capital K. And also we can define KH as KH such that K belongs to capital K and H belongs to capital H. Now the question is that product will be a subgroup. Okay, here the question number 45. Let H and K be any two subgroup of a group G, subgroup of a group G, then the set HK equals to HK such that H belongs to capital H and K belongs to capital K is a subgroup of G. Is a subgroup of G. Now the question is, statement is true or false? Justify. So that means the product of two subgroup will be subgroup or not. So here the answer is the product of two subgroup may not be subgroup. Why may not be subgroup? So here our solution is the above statement is false. The above statement is false. As we will set up one example, one counter example. By using the counter example, what we will show the product may not be subgroup. So as for example, so we need a counter example. If we consider the group symmetry group S3 and H equals to row 0 and row 3 and K equals to row 4, row 0 and row 4. Okay. So what is S3? S3 is the set of all permutation, set of all bijective, you can say the bijective map from the set 1 to 3 to 1 to 3. Whereas you can say also the set of all permutation. This is a permutation group, set of all permutation on the set 1 to 3. On the set 1 to 3. So S3 contains the element row 0, row 1, row 2, row 3, row 4 and row 5. Now the question is here, what is row 0? Now where rho 0 equals to 1, 2, 3, the identity map 1, 2, 3, 1, 2, 3, that bijective map. Rho 1 equals to 1, 2, 3, 2, 3, 1. Rho 2 equals to 1, 2, 3, 3, 1, 2, 3, 1, 2. Whereas rho 4 equals to 1, 2, 3, 3, 2, 1. Sorry, rho 3. Rho 3 equals to 1, 2, 3. So 1 goes to 1 and 2 and 3 interchange, 3, 2. Rho 4 equals to 1, 2, 3, 2 remain same. That will be the fixed element. And 3 are 1 interchange. Whereas rho 5 equals to 1, 2, 3. 3 is invariant here. It is fixed and 2 and 1 interchange. So these are the elements of G. And here you will see, we will take this is the rho 0 is the identity element of the group in this symmetry group. So here then clearly H and K are both subgroup of G. Both subgroup of G. That means the symmetry group S3. But if we calculate HK, that product, that will be rho 0, rho 0, rho 0, rho 0, rho 4, rho 3, rho 0, and rho 3, rho 4. And that set will be rho 0, because this is the identity element. So rho 0 square will be rho 0. And rho 0 is the identity element. So that will be rho 4, rho 3, and next will be rho 3, rho 4. That composition. And you will do the composition rho 3, rho 4. That will be rho 1. So rho 0, rho 4, rho 3, and that will be rho 1. And you will check this is not a subgroup. Is not a subgroup of G, that means S3. Similarly, you also check KH, and KH will be rho 2, rho 3, rho 4, rho 0, and this is also not a subgroup. This is also not a subgroup of S3. If you prepare the composition table, you will see there are some element which does not belong to KH. So closure property does not hold. So from that, we can conclude that the product of two subgroup may not be subgroup. Now the question is, when this product will be a subgroup? Okay, so that is one important theorem. So this is, you can say, the theorem, or is our question number 46. What was the question? Let H and K be any two subgroup of a group G, then HQ is a subgroup of G, then the product HK is a subgroup of G if and only if they commutes. So that means HK equals to KH. If H and K commutes, then under this condition we can say HK is a subgroup of G. But we need to prove the theorem. That is one important theorem. So this is basically a 4 marks question for Calcutta University or any other graduation examination in different universities. So what we will prove? First we will take HK is a subgroup of G, then from that we will prove HK equals to KH. So let HK be a subgroup of G. From that we have to prove that Hk equals to Kh. So now, in which way you will say to set P equals to Q? First we will say P subset of Q, then we will check Q subset of P. Both the condition holds. So from 1 and 2 we can say P equals to Q. Here in position of P you just consider Hk, and in position of Q you just consider Kh. Okay. So what we will show here, we will show first Hk subset of Kh, and also we will show Kh subset of Hk. And that will be our 1, that will be our 2. And from 1 and 2, therefore from 1 and 2, we conclude that what we conclude? Hk equals to Kh. Now the question is how we will show P the subset of Q. So if we show X belongs to P implies X belongs to Q, from that we can write P subset of Q. So here Hk subset of K, that means we will take let X belongs to Hk, and from that we will show X belongs to Kh. Okay. So X is an element of Hk and Hk is a subgroup. So what we can write, since Hk is a subgroup, so from that what we can write, X inverse, this also belongs to Hk. And from that we can write X inverse equals to some H1 K1 for some H1 belongs to H and for some K1 belongs to K. Now if we take inverse on the both sides, so X inverse, that will be H1 K1 inverse, and this implies X equals to K1 inverse H1 inverse. Why? Since X inverse, this will be X, and H1 K1 whole inverse, that will be K1 inverse H1. This is the standard property of the group because Hk is a group. And from that, since H1 belongs to H and H is a subgroup, so that implies H1 inverse belongs to H. And K1 belongs to K, that implies K1 inverse also belongs to K, as H and K both are subgroup. That means X belongs to K. So what we have proved, we have taken X belongs to Hk. What we have shown, X belongs to K. And since X is arbitrary, so what we can write, Hk subset of K. Since X belongs to Hk, this is arbitrary. Okay. Now we'll come to the next part. So here we'll take let Y belongs to Kh. What we will show? We will show Y belongs to Hk. And since Y belongs to Kh is arbitrary, from that what we can write, a Kh subset of Hk. So Y belongs to Hk, then Y inverse belongs to Kh. Why? Because since okay, so what we can do, we can take easily in that way, say will not, because it is not given Hk is a Kh is a subgroup. So what we will do, okay, we'll let Y belongs to Kh. So from that what we can write, Y equals to some K2H2. Okay, for some K2 belongs to K and H2 belongs to H. Okay, and since K2 belongs to K, and H2 belongs to H, so from that we can write H2 inverse and K2 inverse that belongs to KH. That belongs to HK. And why? Because H2 inverse belongs to HK2 inverse. And since HK is a subgroup, since HK is a subgroup, and H2 inverse K2 inverse belongs to HK. From that we can write H2 inverse K2 inverse whole inverse that belongs to HK. And that means, that implies K2H2 belongs to HK. Well, that means Y belongs to HK. Why? Because since Y equals to K2H2. So by using the condition HK is a subgroup, what we have proved? HK subset of KH and KH subset of HK. So that means HK equals to KH. So the first part is done. Now we will move to the converse part. Okay, so this is single start. So conversely, let what we assume, conversely let HK equals to KH. What we have to show here, we have to prove that HK is a subgroup of G. HK is a subgroup of G. That we have to prove. So what we will do, first we will take say, since E equals to E, and that belongs to HK, where E is the identity element, in G, is the identity element in G, and H and K are subgroup of G. So E belongs to H and E belongs to K. Okay. So from that we can write HK is non-empty subset of G. Okay. Now what we will show, we will take two elements, let P and Q belongs to HK. What we have to show, PQ belongs to HK. PQ belongs to HK. And again, what we will take, let P belongs to HK, and from that we will show P inverse belongs to HK. And after that, what we can conclude, HK is a subgroup of G. Okay, so this is the subgroup test. So P belongs to HK, Q belongs to HK. Then what we can write, P equals to some H3K3 and Q equals to H4K4 for some H3H4 belongs to H and K3K4 belongs to K. Then now therefore what will be the PQ? PQ will be H3K3 H4K4. Okay. So that we can write, this is equals to H3 by associativity K3H4K4. And from that we can write H5K5. So H3K4, and that place we can write H5K5. Why? Since K3H4 belongs to KH, and what is the condition is given? KH equals to HK. KH equals to HK. So that means K3H4, this is will be H5K5 because that belongs to HK. So for some, H5 belongs to H and K5 belongs to K. From that we can write H3H5 by associativity K5 K4, and that element belongs to H, and K4 K5 because HK are subgroup, since HK are subgroup of G. So we have proved PQ belongs to H. Now let P belongs to HK, then what we can write? P equals to some H6 K6. What we will show? P inverse belongs to HK. Okay. So now P inverse means H6 K6 whole inverse. So that will be K6 inverse H6 inverse. And that belongs to KH. And again it is given KH equals to HK. This is given. Okay. So what we have shown, P inverse belongs to HK. Since P inverse is arbitrary, so P inverse belongs to HK for all P belongs to HK. So that means HK is a subgroup of G. So product of two subgroup will be a subgroup if H and K commutes with each other. You can only. Okay. So an important note, if G is a commutative group, G is commutative group, and H and K and H comma K are two subgroup of G, then what we conclude? Then HK is also a subgroup, or KH is also, because here G is commutative, so HK equals to KH, that is obviously holds. Okay, but this result may not be true for a non-commutative group. So in the counter example, S3 is a non-commutative group. So now another important result or recall. This is the recall. Let HK be a subgroup of G. Let H and K be any two finite subgroup of G. Any two finite subgroup of G of a group G then what should be the number of element in HK? The number of element in HK, this is the number of elements in the product HK, and that will be order of H into order of K divided by order of H intersection, because HK is subgroup, so H intersection K must be a subgroup. So we can find out the order of H intersection. So how many elements exist in the product HK? That we can say easily. Okay. And so there is one important question. The question is very, very important. This is question number 47. The question is, let H and K be two subgroup of a group G, be two subgroup of a group G such that H has 7 elements, and K has 13 elements. then the number of elements in HK, then the number of elements in HK is option A 1, option B 5, option C 0, and option D 91. Now we'll use the formula or recall the number of element in HK, that will be number of element in H, number of element in K, number of element in H intersection. Now the question is how to find out the number of element in H intersection. So what is exactly given? So here it is given number of element in H is 7, number of element in K is 13. But the question is what is the number of element in H intersection K? First, if we find out this number, then we can find out the number of element in HK. So how to find out number of element in HK? So what we know, what is our recall? So the recall is H intersection K obviously is a subgroup of G. Subgroup of G. Why? As H and K both are subgroup of G. And therefore, if we use the Lagrange's theorem that we will prove today, Lagrange's theorem says as order of H intersection K, it must divides order of H. Why? Because it is a subgroup of H also. And H intersection K, that order again divides order of K. And from that, if A divides B and C divide, A divides C also, so GCD of AB must divide C. So from that we can write, so H intersection K, that order must divides GCD of order H and order. Okay. So here we have used the recall. A divides B and A divides C. So that implies A divides GCD of B.Sc. So that means here GCD of order of H is 7 and 13. This is basically 1. So therefore what we can say, order of H intersection K, this will be 1. So that means here H intersection K is basically subgroup and it contains the identity element only. Okay. So what will be the answer? The answer will be what we will know. H, the order of H is 9, order of H is 7, and K is 13 by 1. So that will be 91. So option D is correct. All other options are again, there is another important fact that we will prove with the help of Lagrange's theorem. But okay, before that we will solve the Lagrange's theorem and then we will prove. So here question 48, and that question asked the Calcutta University examination 97, 99, 2001, 2003, 2005, and so on. So this is one of the important question, very, very important. What was the question? The question is state and prove Lagrange's theorem for a finite group. State and prove Lagrange's theorem. Lagrange's theorem for a finite group. For a finite group. And this is basically 2 plus 4, 6 marks. For statement, you have given 2 marks. So first we'll come to the statement. and then we will prove it. So statement is, let G be a finite group. Let G be a finite group and H be a subgroup of G. And H be a subgroup of G. Then the order of H must divide. Then the order of H must divide the order of G. Simple. Or you can say in that way, or the order of every subgroup, the order of every subgroup of a finite group G is a divisor of order of G. Is a order of every subgroup of finite group G is a divisor of the order of G. Of the order of G. The same statement. If G be a finite group and H be a subgroup, then order of H must divide order of G. And the question is how to prove the statement. So what we consider here? We consider H is a subgroup of G. So let H be a subgroup of the finite group, G. That we assume what we will show, order of H is divides order. So let we consider order of G equals to n, as order of G is finite, so we can take any finite number, say n. And let us consider all of the distinct left coset of H in G. Okay, so G is a group and H is a subgroup of G. So we consider all left coset. We consider the set of all distinct left cosets of H in G. Okay. So now the question is, since order of G is finite, order of G is n, so number of distinct left coset, so number of distinct left cosets of H is finite. Okay, and say therefore there exists an element, say x1 comma x2 dot xm in G, m obviously less than equals to n, in G, such that x1h x2h dot xmh is a complete list of distinct left coset of H in G. So now it is obviously clear where m is obviously less than equals to n. This is very clear statement. Since all left cosets are distinct, all left cosets are distinct, and we know if the left coset are distinct, so if any two left coset are distinct, then they are completely disjoint. So obviously they are disjoint. They are disjoint. We know the theorem. The left coset are either disjoint or identical. Okay. So this is by the theorem as any two left coset or right coset are are either same or disjoint. So as they distinct, so we can say they are disjoint. So that means that is what we can say XI-H intersection XJ-H. It is completely disjoint phi for all I not equals to j, and I comma j belongs to 1 to up to n. That we can say. So therefore we can write G equals to union of I equals to 1 to m XI-H, that union. As G is partitioned into distinct left coset of H, this is G, so this is X1H, they are all distinct left coset, X2H, X3H, and XMH, XM minus 1H, and so on. So as they are distinct, so as G is partitioned into distinct left coset, into distinct or disjoint left cosets of H. Okay. Now we will apply one important theorem. The theorem is each coset has the same size as H. Okay. And from that we can write, since each left coset in fact left cosets has the same size as H. Why H also we can consider EH, where E is the identity element. So from that what we can write, order of G, that will be summation of XI-H I equals to 1 to m. Okay, because they are distinct. So you know, if the set C equals to A union B and A or B are basically disjoint, so from that order of C equals to order of A plus order of B when if A intersection B equals to 5. So here we have used the result, and from that, because they are same size as H, so we can write, so M, so this will be a cardinality of X1H plus cardinality of X2H plus dot 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 cardinality of XMH. Now what I said, all the left coset has the same size as H, so you can write H plus cardinality of H plus cardinality of H, and that will be, this will be M times. So what we can write, M into order of H. What is M? M is basically a natural number, and from that what we can write, so order of G equals to n, this will be m into order of H, and that means order of H must divide n, because since m is an integer, order H divides n, that means order of H, it divides order of G. Why? Because since n equals to order of G. So what we have proved, order of H is a divisor of order of G, of the order of G. That means every subgroup, order of every subgroup is a divisor of order of G, since H is arbitrary. So this completes the Lagrange's proof of the Lagrange's proof of Lagrange's. So this is quite simple proof, and by using this result, we can say, okay, this will be okay. Now the question is the converse true? Is the converse true? That means for every divisor of the order of G, there exists a subgroup of that order. Okay. So if you have asked the question, this is question 49, is the converse of Lagrange's theorem true? Okay, answer is no. The converse is not true. So converse of Lagrange's theorem, what exactly mean by that? Let the converse part, let G be a finite group, then for every positive divisor of the order of G, there exists positive divisor, say D of order of G, there exists a subgroup of order D, and our answer is no, there does not exist this kind of relation. Okay. So you can set up the example. For every positive divisor of G, there does not exist a subgroup. Okay. So okay, you can set up the example, but the thing is, okay, so we need example. And this is your exercise. You will show one group of finite order, and also that order divides D, divides the order of G, but okay, for that order we can't find out any subgroup. Okay, so you need to produce that kind of example, and this example is also much important for the examination purpose. Okay. So now the question is, when the converse of the Lagrange's theorem will be true? When the converse part of Lagrange's theorem is true. The answer is if the group is cyclic or abelian. The answer is if G is finite cyclic group, then the converse part is true. Okay? Or maybe the group is abelian. On that case, the converse is true. So this kind of example exactly help us. This kind of concept help us to give some answer in some indexed questions. So now we'll define here the index of a subgroup. What exactly mean by the index? That recall is important. Index of a subgroup. What is meant by the index of a subgroup? Let H be a subgroup of a group G, then the index of H in G, then the index of H in G is denoted by G index H in that symbol, and is defined by G index H. This is equals to the number of left cosets of H in G, or you can say the number of right coset. Either you will take left coset or you will take right coset of H in G. But the thing is, there is a theorem, and that we can draw from the Lagrange's theorem. We know if G is finite group. Till now we don't know G is finite group or not. But okay, if G is finite group, then we can find out easily what should be the G index. If G is a finite group, then and H is a subgroup of G, and H is a subgroup of G. So because of finiteness, we can find out the index of H in G, that will be order of G by order of H. Why? Because since order of G is finite, and that also implies order of H is finite. And by Lagrange's theorem, what we can say, order of H must divide order of G. So this is also a nice application of Lagrange's theorem, and you can find out easily the number of left coset or number of right coset of H in G. So now we'll come to some important question. The question is question number 50. The question is very, very important. Let G be a group. Suppose G has a subgroup of order 45 and 75. And if order of G is less than 400, then what we can say, then order of G is equal to option A 90, option B 150, option C 225, and option D none of the above. This kind of question you have asked in different competitive examination or in the course Calcutta University Mathematics Honors or any other university Mathematics Honors. So there is one important recall. First I will draw your attention in the recall, then we will solve the answer. Let H and K be to subgroup of a group G, be to subgroup of a group G, then by Lagrange's theorem, what we can say, order of H divides order of G, and order of K is also divides order, because they are the subgroup. And from that we can easily say LCM of order H and order K, that LCM must divide order of G. Okay. So now we just use this result. Here G is a group and obviously the finite group. So you can apply the Lagrange's theorem. So since order of G less than 400, that means order of G is finite. And H and K are subgroups. So here let order of H, this is basically 45, and order of K equals to 75, where H and K are subgroup of G. then what we can say, the LCM. So then LCM of order H, order K, order H and order K that divides order of G according to this result. So what will be the LCM? LCM of order H and order K, that means LCM of 45, 45 and 75, and that will be 225. So 225 divides order of G. And from that, order of G will be 225 multiple sum K for some K belongs to natural number. So this is the relation. So now if we put K equals to 1, so order of G will be 225. If we put K equals to 2, order of G will be 450. And 450 is not less than 400. But this is less than 400. So this is the only one case. That will be the valid case. So obviously option C is correct and all other options are false. So this question is very much this very important questions. Okay. Now we'll come to another important question. Question number 51. That question is also important. Let H and K be any two subgroup of a group of a finite group G, such that order of H equals to P and order of K equals to Q, where P, Q are distinct primes. Then order of H intersection K is option A 1, option B 2, option C P, option C Q, and option D PQ. The product. So here, what I said, since HK are subgroups, H intersection K is also subgroup of H and K. So that divides order of H, and H intersection K, that order also divides order of K. And from that we can write H intersection K, the order of this subgroup, the intersection, must divide GCD of order of H and order of K. So that means H intersection K, that order divides GCD of, what is order of H? P and Q. And PQ are distinct primes, so for any two distinct primes, we can say they are relatively prime to each other. So GCD of PQ must be 1. So order of HK equals to exactly 1, because order can't be negative. So it can't be minus 1, it will be 1 only. So that means exactly H intersection K, this is a trivial subgroup, just contains the identity element of it. So option A is correct, all other options. So in position of P, say you have given H equals, order of H equals to 7, order of K equals to 11. So what should be the order of H intersection K? Again it will be 1. Because the GCD of 7 and 11, this is basically 1. Okay. So thank you so much. And next day we'll continue from question number 52 and so on. So today we finish the product subgroups and the Lagrange theorem. And this is very helpful in the graduation course and as well as the comparative exam.